Okay. Well, it's a great pleasure to have Dan Brown visiting us virtually from University College London. Thanks, Dan, for agreeing to give this this talk. And we look forward to hearing about universal fault-tolerant quantum computing with three-dimensional surface codes. So I'll let you begin.
Thanks very much, Tenjo. So I'm going to talk about some of the recent research in my group, and I appreciate this is a very diverse audience, and some of you have probably heard quite a lot about quantum computing before. Others of you maybe haven't heard so much. So I've tried to sort of balance that in my talk with sort of different levels of technical detail. But if there are any questions that people have during the talk, I'm very happy to stop and answer them. Also, it makes me feel a little bit less like I'm just giving my talk to my laptop. So please do interrupt if you'd like to ask any clarification.
People can unmute themselves, but if you do, please mute yourself again once you've finished. Okay.
So
thanks.
Let me start with just a few words about where quantum computing is right at the moment. And it's quite an exciting point. The technological development of quantum computers is making rapid strides, in particular with quite significant interest and investment in industry. And you probably have heard and read about the recent experiments in Google, who demonstrated a prototype quantum computing device with 54 qubits. So a qubit, as you probably know, is the quantum analog of a bit. And we can think of that abstractly as a two-dimensional state space where our qubit can inhabit any state corresponding to any vector in that complex state space. And if we have n qubits in our quantum computer, the size of that state space grows exponentially as we glue together these state spaces with the tensor product. So already the chip that Google has demonstrated has a eye-wateringly large state space. So these states are inhabiting approximately 2 to the 16 dimensions. And just for comparison, one of the world's most powerful supercomputers, the IBM Summit, has in its memory about 10 to the 18 bits. And it's actually worth mentioning IBM Summit because after Google announced their result with great celebration and claiming this as a big breakthrough, a demonstration of what they call quantum supremacy, essentially doing something that would be beyond the capabilities of our best supercomputers to replicate, IBM did point out that their Summit supercomputer might be able to compete, but it would still have been more, it still would have been slower than the Google chip for performing this task. So quantum computers have reached this very exciting stage where they can start to do things which are very challenging for even the most powerful supercomputers. And in some sense, oops, I need to change slide, okay. In some sense, the field is moving along two paths at the moment. On the one hand, the very exciting possibilities of using these machines that have been developed. Now, the devices are not perfect, and for all sorts of reasons, there are noise and error. This can be to do with control errors. It's often to do with decoherence due to the interactions between the qubits and their surrounding environment. So at the moment, there's a lot of excitement in the possibility of trying to use those chips to do experiments and to deliver applications. And this approach to quantum computing is called NISQ, N-I-S-Q. It's a name that was coined by John Preskill. And that stands for noisy intermediate scale quantum computing, where we're not doing any error correction. And I like to think of this as sort of analogous to analog TV versus digital TV. So the analog TV that we grew up with was very, very noisy. And of course, once it was replaced with digital transmissions, all of that noise went away. Now the quantum computing analog of the digital broadcast is fault-tolerant quantum computing, where errors are suppressed using error correction. And that comes at a cost. It comes at several costs in terms of the complexity of the implementation, but in particular, you will end up needing at least thousands of physical quantum bits to represent each quantum bit in your computation due to the redundancy in that error correction. So you can see already the fault-tolerant quantum computing is a little bit beyond the capabilities of the current hardware. Nevertheless, it is certainly where quantum computing would like to reach to meet its full potential. And in particular, we now know theoretically that using fault-tolerant techniques, any of these noise and error sources, if they're sufficiently controlled within the device, error correcting techniques can be used to suppress this error almost arbitrarily low in most circumstances. So this fault-tolerant paradigm of quantum computing is something that this particular talk is focusing on. So quantum circuits are the way we describe, or both the way we describe quantum computations and the way we typically would seek to implement them. And typically you will have a register of qubits upon which you perform computation via unitary quantum logic gates. So these are unitary transformations on single qubits, on multiple qubits, and together they compose to implement the computation that you desire. At the end of the computation, you need to read out the result of the computation back to the classical world, and this is accomplished by a measurement. And typical architectures for quantum computers realize their quantum circuits using a universal set of logic gates. So that's a set of gates which can be composed to generate arbitrary unitary transformations on the qubit register. And this is very analogous to the way a NAND gate is a universal gate in binary logic. But in practice, of course, we have noise. So every physical operation that takes place within the device, and even just the storage of the information, is prone to errors. And those errors will degrade the computation. And it does pose limits on what can be achieved without error correction in place. So the paradigm of fault-tolerant quantum computing has been created based on ideas from classical error correction, and similar sorts of error correcting codes are now used widely in digital data transmission and classical computing, together with techniques to avoid error spreading and keeping them under control. So I wanted to just begin my talk with just a few illustrations of some of the basic ideas of quantum error correction, because I know many of you won't have heard about this before. And it's really based on some very simple principles. First, the principle of redundancy. So this is illustrated by this simple example of a repetition code, where we're encoding the value of a single qubit across 3 qubits. And we do this in this very simple way by representing our 0 state with 3 qubits in the 0 state, and our 1 state with 3 qubits in the 1 state. And you see how, if we now have an error on the data, so for example, let's imagine that the value of the middle bit is flipped, the middle qubit, and that transforms the state, as you can see on the right-hand side of the screen. But you could recover the original state, and you can detect that error in ways which don't destroy the quantum superposition. And the way you do this is using a parity measurement. So here's an example of a quantum circuit which does this, which illustrates some of the tools we use. We can use controlled NOT gates, which controlled upon the value of one of the qubits, perform a controlled flip on the other qubit. And what that allows you to do in this particular circuit is measure the parity of two bits. Essentially, if the two qubits are of even parity, so they're in state 0, 0 or 1, 1, there will either be 0 or 2 flips of this ancillary qubit. such that when you measure it, you'll measure 0. Whereas if one of them were flipped, the measurement outcome will be 1. And so this allows us to detect the sorts of errors that could flip a single bit like this, to detect this error without collapsing the state entirely and destroying the coherent superposition alpha 0 plus beta 1, which is the thing we want to preserve. And basically, quantum error correction uses variants of this simple idea of parity measurement to detect the errors and correct the errors in the quantum computer. And there is a convenient way of representing these parity measurements is with Pauli operators. It turns out that Pauli operators are the perfect mathematical objects for studying quantum error correction. And it's rather quite beautiful how we use all of the many nice and unusual properties of Pauli operators to implement different aspects of quantum error correction theory. I just draw your attention to the fact that the Pauli operators are n-fold tensor products of the standard Pauli matrices, often written sigma x, sigma y, sigma z in physics, but we use them so often in quantum computing theory that we drop the sigma and just write x, y, and z. And these matrices have the special property that they're both unitary and Hermitian, which in the context of quantum computing means you can think of them as logic gates. So remember that the logic gates are all unitary transformations, including, for example, errors that can occur. So the Pauli matrices can represent errors, but they're also Hermitian operators, so they represent observables, so things we can measure. And it's very useful that we've got these single mathematical objects with both the errors and the measurements we make. These operators also form a basis for linear operators on our n-qubit space. And that's also extremely useful. It means, for example, that any general error can be written as a linear combination of Pauli operators. And that has the useful practical consequence that it means that if you're able to correct Pauli errors, it turns out that you can also correct linear combinations of Pauli errors. So we can convert what would be a very complicated error correction problem, where we would have this fearsome, exponentially large, continuous range of possible errors, converts it into a discretized problem where we're just correcting for Pauli errors. And similarly, we can also use these Pauli operators to represent our states. So they're extremely sort of useful parts of the quantum error correction toolkit. So if we go back to our parity measurements, we can describe this as a measurement of the observable Z tensor Z. And if you were to look at the eigenbasis of that observable, you'll find that corresponding to the +1 eigenvalue, you have the 0, 0, and 1, 1 states. Corresponding to the -1 eigenvalue, you have the 0, 1, 1, 0 state. So measuring this observable is equivalent to performing the parity measurement that I described. And I can demonstrate with some concrete examples how the error detection works. So imagine that we have an error on the middle qubit here. So it flips the value of the middle qubit. If we then measure the parity of of these two pairs of neighboring qubits, we find that for this particular error, both of these measurements will record a 1 output, which is an odd parity. And we can see that explicitly in the state that these neighboring pairs of qubits are all in an odd parity state for this particular error. But for example, an error on the bottom qubit will only leave the last two qubits in an odd parity state. So we can distinguish these different measurement outcomes and use them to identify the error. So this is known as the error syndrome, and it identifies the errors that have occurred. And now the Pauli operator formalism gives us a very simple way to understand how this works. And what you can show is that if the observables you're measuring to detect your errors, and I'll call these check operators, if those observables are Pauli operators, they will detect precisely those Pauli errors which anti-commute with them. So these tensor products of Pauli operators will either commute or anti-commute, and that gives us a very simple rule to know how errors and the output of our check operators are related. So it's a very sort of simple mathematical idea which underlies how quantum error correction works. And in particular, the rule for the commutation rule for tensor products of Pauli operators is a very simple one. So if we take two tensor products of Pauli operators, they will commute only if a even number of their tensor factors anti-commute. So for example, in this example I've given here, we have x tensor x and z tensor z. Those two operators commute because they have two tensor factors which individually anti-commute, and there's an even number of them. So it's very easy to use this formalism to understand error correction and design new codes. Now, in particular, I mentioned already that if we can detect and correct Pauli errors, we can detect and correct general errors. But actually, it's even simpler than that, because the Pauli Y operator can be formed as a product of the x and z operators. And that means that if we can correct both x and z errors, we can treat a y error as a z error followed by an x error, and we can correct that too. So all of error correction and detection for very general families of errors boils down to just detecting and correcting Pauli X errors or Pauli Z errors. And the CSS, or Calderbach, Schorn, and Steen approach to error correction breaks down the error correction problem into these two distinct problems. One of them is to detect and correct X errors, the other one to detect and correct Z errors. And in the first case, we do this by measuring observables which are tensor products of Z. And in the second case, we do this by measuring tensor products of X. So I'll call those Z checks and X checks. So now we can introduce the surface code. And first, I'll introduce the two-dimensional version of the surface code, which is the one that is most studied. So this was introduced by Kitaev in 1996. It's very closely related with the quantum double models, which have been studied in condensed matter physics and in the context of lattice gauge theory. It is defined on this two-dimensional grid on which we can identify edges, vertices, and plaquettes. And the code makes use of each of those three types of geometric objects in its definition. In particular, we imagine that with every qubit in our code, we associate an edge on this lattice. So each of the edges in this diagram here are representing qubits. And then the error checks are defined in terms of the vertices and the plaquettes. So for every vertex on the lattice, we construct a Z check consisting of Zs on only those qubits adjacent to that vertex. And similarly, we construct X checks where we construct a tensor product of X operators around the edges of a plaquette. And we do that for every vertex and every plaquette on the lattice, and that defines the surface code. And you can show that it will allow you to detect and correct general errors on single qubits, and indeed clusters of errors which are sufficiently localized within the lattice. So in practice, it works extremely well at detecting and correcting errors as long as those errors are sufficiently sparse across the lattice. And because of this, it has become the leading architecture for fault-tolerant quantum computing. I mean, there have been a wide variety of approaches to quantum error correction proposed, which I don't have time to talk about, but the surface code stands out as being particularly straightforward to implement. So those error check operators that I described in the previous slide are very low weight, so they only involve 4 qubits. There's a regular modular structure, so all of these error checks look very similar to one another. And so if you're actually designing a quantum computing chip, you'll be repeating the same sort of structure throughout the architecture. And also they work very well, as I've already mentioned, so we can quantify somehow the robustness of a code family with respect to errors using the error threshold. So this, if we take a simple error model, what this threshold tells us is the highest error rate at which increasing the size of the lattice will suppress the overall logic error rate after we've performed our error correction procedure. And the threshold for the surface code is approximately 1%. And that means if in the construction of these devices, if the error rates can be brought below around 1%, then errors can be arbitrarily suppressed by increasing the size of the lattice. And that's the key idea behind using these sorts of codes. You make your lattice large enough so the error is suppressed down to the level that you need. So although they are the leading architecture at the moment, there are still so many challenges. And in particular is this very high overhead. So I already mentioned that you require thousands of physical qubits per logical qubit. And indeed, as you make your lattice size larger, the number of encoded qubits remains at 1. Now, this is very different to the sorts of error correcting codes that are typically used classically, where typically as you use more and more bits for your encoding, you also are able to encode more and more data bits.
Sorry, Dan, where does the 1000 come from?
So this 1000, I should say, is a rough estimate that was made in a full sort of simulation by two of the researchers from the Google team on what would be the requirement for a quantum computer that would be able to outperform the best classical computers for a factoring problem. So they were studying a particular challenge problem in implementing Shor's algorithm for factoring, and they estimated to get the noise levels low enough in their particular architecture, they would need thousands of physical qubits. But there have been other estimates. All of these numbers should be taken with a slight pinch of salt, but they give you an idea of the sort of order of magnitude.
But are they not architecture dependent and how the...
Yes. So this depends
very strongly architecture dependent.
It is strongly architecture dependent. So this is just gives you a flavor. So in that estimate, they made certain assumptions. I would say they were rather optimistic assumptions. So certainly this overhead is likely to be high, and other people have made other estimates with other models where you could be tens or even hundreds of thousands of physical qubits per logical qubit. It all depends on the error rate on the device. Whatever.
Nevertheless, this is much better than the CSS, is it?
So no, this is an example of a CSS code.
All right.
The CSS codes are the codes where the X errors and the Z errors are independently corrected. So that's one of the overheads, and there is ongoing research to try and find alternative approaches which improve on that, taking inspiration from in classical error correction, where, for example, people use low-density parity check codes which don't suffer from that problem. But I'm focusing in this talk on a different overhead which also arises here, and that is that this particular code has a very small instruction set of native gates. So the logic gates you can implement on the surface code in a native fault-tolerant way are very limited, and that creates its own overhead. So I'll say a few words about how we want to implement our logic gates to implement our computation. And I said we wanted to do so in a way that doesn't cause errors to spread, because errors that spread, correlated errors, are not well corrected by our codes. And one idea is to use what are called transversal gate constructions. And basically what that means is that when you implement your logic gates, the physical interactions that you use to implement those gates, each individually acts on only one physical qubit in each encoded qubit. So I'd imagine if I wanted to do a computation with 2 encoded qubits, I'd take 2 lattices, and my transversal gates, each gate that I applied would act most on 1 physical qubit in each of these 2 lattices. So this is an example of a transversely encoded CNOT. And oops, sorry. And So that little blue window was not supposed to pop up just yet. But so for the surface code, as well as the C0 gate, we can implement the Pauli operators transversally, but that's about it. So the gates we have is very, very limited. We can implement C0 gates, we can implement Pauli operators, and we can make measurements of Pauli operators. But that is not a universal set for quantum computing, and in fact, it's not even a universal set for classical computing. It's very rudimentary in what it can do. Now, remarkably, that is still enough for universal quantum computation with an extra ingredient, which is something called magic state distillation. And the details of this slide don't matter too much, but basically the idea is you can augment your gate set with other gates, which you implement without error correction on an ancilla state. And there's a way of taking the state produced by applying this gate to an ancillary qubit and purifying it and then using it to implement the gate that you want. And remarkably, the only native gates you need for this process are Clifford gates and Pauli measurements. And this is called magic state distillation, but it's horribly expensive. So in another paper, there's a very nice model of fault-tolerant quantum computation, which is estimated as natural numbers. They estimated, again, for a sort of a Shor's algorithm factoring problem, you might need 6.3 million of these ancilla qubits to implement this magic state distillation. So that's this huge overhead of 6.3 million qubits just because you don't have a universal gate set as your native gates. So what we'd like to do is find error correcting codes which share many of the practical advantages of the two-dimensional surface code, but which have a broader range of native gates. Now, there's a nice way of characterizing the different families of quantum logic gates, which is called the Clifford hierarchy. So the Pauli operators sit at the bottom of this Clifford hierarchy, and we form this hierarchy of operators by considering how the Pauli operators themselves are transformed when they are multiplied with, or more precisely, when they're conjugated by other unitary operators. And the technical details of this don't matter, but what's important is that when we get to level 2 of the Clifford hierarchy, we're restricted to quite a modest range of operations known as the Clifford group. And one of the properties of the Clifford group is that Clifford group circuits can be efficiently classically simulated. So the Clifford group is not universal. But it turns out that if we add any gate from the 3rd level of this hierarchy or higher, we can get universal quantum computation. So that's what we want, a native gate from the 3rd level of this hierarchy, which together with the Clifford group will give us a universal quantum computer. And the reason I mention this hierarchy is that there's a beautiful theorem by Bradley and Koenig from 2013, which shows a relationship between the level of the hierarchy that you can reach with your native gates and the dimensionality of the code. And in particular, they proved that if you have an n-dimensional topological code, your fault-tolerant gate set will always lie in the nth level of the Clifford hierarchy. So that means that with a 2-dimensional surface code, you're never going to get beyond the Clifford group because that's level 2 in the hierarchy. You're never going to avoid magic state distillation and its associated overhead. So what did we consider? Well, we looked at the next dimension up, and we considered the 3-dimensional version of the surface code. And what we showed is that you can indeed achieve a gate in this 3rd level of the Clifford hierarchy and realize a universal set of native gates in this 3-dimensional code. So how do we go from a 2-dimensional surface code to a 3-dimensional surface code? Well, it turns out that in Kitaev's original formulation, these cases were already included. So he used a very general framework to define these codes using homology theory. So those of you who are familiar with homology will recognize the technical terms that are popping up on these next slides. But those of you who don't, it's a very beautiful branch of mathematics which combines group theory and topology. And it's constructed from the idea of boundary maps which connect objects of n-dimensional objects with n-1 dimensional objects. So for example, the boundary of a cube would be the 6 faces, which are the surface of the cube. The boundary of a square will be the 4 edges around the square, and those edges themselves are one-dimensional objects. The boundary of every single line would be the vertices at the end of that line. And homology theory constructs a beautiful mathematical theory abstracting these concepts. And Kitaev used homology to define these codes. So the X checks are actually defined as the boundary of the faces, the 2-dimensional objects, and the Z checks are the co-boundary of the vertices. So co-boundary here just means the edges of which a particular vertex is in the boundary. So we can see this vertex is in the boundary of these 4 adjacent qubits. And because homology can be applied to a wide range of spaces, and in particular a wide range of lattices, this immediately generalizes to other dimensions. So we can lift up to 3 dimensions, and now we find that our X checks are defined as the boundary of these 3-dimensional cells, so cubes in this example, and the Z checks are the co-boundaries of edges, which means 4 faces adjacent to each edge in the lattice. And you see we've chosen here to place our qubits on the faces of this 3D lattice. So we want to try and construct a native 3rd level of the Clifford hierarchy gate for this 3D code.
Excuse me, what does the word native mean here?
So native, so that I haven't specified that, but what I mean is, I mean, in particular, we're going to show a way of realizing the gate using a transversal operation. So that means that you're not using any ancillary qubits and you're acting unitarily. And there are slightly more general notions of what is a reasonable definition of a native gate, which were used in Bravyi and Koenig's theorem. But I would think of it as being realized by unitary gates rather than by the preparation of ancillary qubits.
Yeah. Another question, do you keep track of the orientation? Or do you...
The orientation in these lattices is not so important in this case because we're working with qubits, and so the underlying group
I mean in homology, you either can do it over Z, and in this case you need to give an orientation to every edge or face or so.
Exactly. So yes, in general, in the general case you do, but in the qubit case the group is Z2, so that is not necessary.
Thank you.
But the construction does work in the more general case and gives you a even broader family of codes.
Yeah, thank you.
So, but also on the previous slide, like yes, you had stabilizers. So can you explain how this X stabilizer, Z stabilizer look like in this 4-dimensional cube, right? It's I don't know, maybe other people yes, understand it, but my impression was that you didn't kind of explain it. So, but it's very interesting, right? How it works in a...
So in the 4-dimensional case, it's actually quite analogous to the 3-dimensional case. So both of the X stabilizers and Z stabilizers, so I was calling those X checks and Z checks earlier in my talk, both of them are similar to the boundary of cubes. So also the co-boundary of edges in 4 dimension is something which has a sort of a similarity with a cube.
But so, not quite, right? So it's slightly more complicated, but yeah.
Yes. So I'm not going to talk much about the 4D code here. I just
Okay.
added it as an example for fun to think about, but it is very beautiful. And
but is it worked out, saying, are there a publication about this kind of 4-dimensional cube case, right?
So actually the 4-dimensional code has been studied more than the 3-dimensional code. And the 4D code has a number of very beautiful properties, but the challenge of realizing a 4-dimensional code in a 3-dimensional world means that it hasn't really been explored experimentally. But many of the things I'm going to say about the 3D code could be generalized to the 4D code.
Okay, thank you.
So the particular gates we're going to realize on the 3D code are in this family, which I call the CZ family. And this is a family of gates going down the Clifford hierarchy. It starts at the top with just the Z operation, that's the Pauli Z. And then the next layer down is the CZ, or controlled Z. And this has the following action on the basis states. It leaves all basis states invariant, acting on 2 qubits, except for the state 1, 1, which is transformed to -1, 1. So it has its phase flipped. I mean, similarly, there's a 3 qubit CCZ, or double controlled Z, which very similarly has the phase flipped if and only if all 3 bits are in the state 1. And the CCZ gate is the gate we want to achieve in our 3D codes, because this will give us a universal set combined with these other 2 gates and with Pauli measurements. So to give an outline of the rest of the talk, I'm going to give a sort of an overview of the techniques used to derive this result, and in particular some of the geometric ideas that we used. I want to start by first illustrating a 2D analog of the result. So in the 2D code, you might have noticed that this 2-dimensional lattice has asymmetric boundaries, and in particular on the top and bottom the boundary is smooth, with the edge of the lattice coinciding with the edges of the cells or plaquettes, whereas on the other 2 sides it's a rough boundary and the edge of the lattice does not coincide with the edge of cells. And that asymmetry is very important in defining the code, and it's necessary to define the code. And it turns out that these boundaries also define logical Pauli operators. So a logical X operator can be implemented by a string of X's along a smooth boundary, and a logical Z Pauli can be implemented by a string of Z's along a rough boundary. Now, we want to implement a CZ transversely on this code. So it's worth looking at how the CZ transforms the Pauli operators, because this gives us an idea of the structure we want to see in our realization. And actually the transformation is very simple. So the CZ gate commutes with the Pauli Z because it's a diagonal matrix, and so leaves it unchanged when we conjugate the Z operator by CZ like this. But it transforms the X operator. And the X operator is transformed very simply. An extra Z is tensor Z factor is glued on to the X that we started with. So this structure will be realized in an implementation of the gate on our code. And what we can do is we can take 2 copies of the code, but with slightly different properties. So the first copy of the code is as I've introduced. The second copy of the code is rotated through 90 degrees. So you can see as we take our lattice and rotate it 90 degrees, we map edges to edges on the lattice. So that means we've mapped qubits to qubits. So every qubit in the first lattice is associated with a qubit in the second lattice. We've also transformed our rough edge into a smooth edge, and our smooth edge into a rough edge. And this represents a duality between the 2 lattices, which is a very powerful tool. And in particular, when we've made this rotation, the logical Z operator on my first code is lying exactly underneath the logical X operator of my second code. It's lying in the same place. It's physically located in the same place. And my logical X operator of my first code is lying in the same place as the logical Z operator of my second code. And this is necessary to achieve a transversal CZ gate. Because to remind you, the CZ gate, what it's doing, the way it transforms these logical Paulis, is it converts X into X tensor Z. So what we do is we take a stack of these two, we take these two codes and we sort of think of stacking them on top of each other, and then between all corresponding pairs of qubits, we implement the CZ gate transversally. So I've just drawn 4 copies of the CZ, but you should imagine that these pairwise CZs are going on between all corresponding pairs of these two codes. And what does this CZ do? Well, we've seen that the CZ takes an X and it glues another Z onto it. So this transforms this operator previously, which was just X, 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 X on the top code, into X tensor Z, X tensor Z, X tensor Z, which is precisely the encoded version of Z1 times X2, which is what our CZ gate should do. And if you go through the details, you can show that the code space is preserved by this transformation, and the logical operators are all transformed in exactly the right way. So for this construction to work, we needed 2 different codes which had very special compatibility between them. So we had a smooth, so where we had a smooth boundary on the code 1, we had a rough boundary on code 2, and vice versa, and there was a one-to-one correspondence between the qubits. So this is the structure that we're going to generalize to 3D. And so the first thing we considered is to try and generalize that structure in a very obvious way. So first, it's worth having a look at what changes in 3D with respect to these logical operators. And actually, it doesn't change very much. The most important thing that changes is that one of our logical Pauli operators rises up a dimension. So it's no longer a string, it's now a membrane. And actually we have an asymmetry between these 2 types of logical operators. Our logical Z is still a string, but our logical X is now a membrane. And similar to our 2-dimensional code, we again have rough and smooth boundaries. Our logical X membrane is lying along the smooth boundary, and our logical Z is a string along the rough edges. So you can think of the structure of this, the boundary structure of this, being a bit like a tin of soup, like a cylinder, where we have our smooth edges at the top and bottom, and a single rough edge wrapping all the way around. So in order to realize the transversal CCZ, we want, again, for our logical Pauli operators to transform in the same way. And we can do the same calculation we made before with our CZ and see how these operators are transformed under conjugation. And what we find, again, is a kind of a gluing. It's a slightly more complicated gluing. So X now glues onto this linear combination of the Zs acting on the other 2 qubits. And what this means in terms of the geometry that we need, the compatibility we need between our 3 codes, is that if we take the logical X on one code, it needs to coincide with the membrane that would be created by the 2 strings of Z operators on the other 2 codes. And if you just sort of look at it, it looks quite optimistic that just taking your code, taking your lattice and rotating it 90 degrees in 2 different orientations would be exactly what you needed. Well, of course, life isn't quite that simple, and that doesn't work. These lattices do not map into each other when you rotate them 90 degrees. And you can see that just this illustration of the 2 different types of surface show that one does not map nicely into the other. So we needed to take a different approach, and we needed to sort of take apart the geometry of the problem and the structure of these lattices. We wanted to find 3 codes such that, and 3 codes defined on 3D lattices, such that in the first code, the smooth boundary of the first code coincided with rough boundaries of the second two codes, and vice versa and vice versa. So we want families of 3 different lattices which have this nice compatibility between their boundaries. And so how did we find this? So we found a very useful tool was to switch to a different picture. So to go away from Kitaev's homological description of codes and have a different lattice representation. And we did what's known as rectification, which is where you take a lattice and you convert faces into vertices. And that's very natural for us because now our qubits are living on vertices. So we made the rectification of this lattice, and we found that we achieved something called the rectified cubic honeycomb. So this is quite an interesting lattice. It forms a uniform tessellation of 3D space. You can build it out of octahedra and cube octahedra, and importantly, it's 3-colorable, which you can't see very clearly on these 2 pictures, but you can see on this other representation. And the 3-colorability is really important, and it was sort of the key to unlocking this problem. So with this new representation of the lattice, and I stress it's the same lattice represented in a different way, or it's the same code represented on a different lattice in an equivalent way. And instead of the homological definition of our x checks and z checks, we find that there's an alternative definition in this lattice which uses the colorings. And the x checks are defined by the red cells in this 3 coloring, whereas the z checks are defined as the faces between pairs of yellow and green cells. So we've used all 3 colorings in our definition, but in an asymmetric way. And that immediately suggests that we can look to find other codes by using the other colorings. So we define our x checks by cells of 1 color and our z checks between faces of cells of the other 2 colors. And this gives us 3 different codes with different sets of x checks and z checks, but crucially, all of which have qubits which are represented by vertices on the same lattice. So we've still got the one-to-one mapping between all of the qubits in each of the 3 codes. And we wanted to find codes such that the smooth boundary in one coincides with the rough boundaries of the other 2 codes. And how do we check this? Well, we need to construct our boundaries. To do that, we went back into the Kitaev's homological picture. So now we've got our new codes. We can then rewrite the code description back in the homology language by finding another lattice to do that. And it turns out it's the rhombic dodecahedron lattice, which in Kitaev's picture gives you our 2 new types of codes. So putting that all together, we were able to show that it does indeed work. So we could find common boundaries, which are smooth boundaries on one of the lattice, but rough boundaries on the other 2 lattices. And that was in precisely the ingredient we needed, as then the construction for the CCZ went straight through, and we were able to show that indeed, if we construct these 3 types of lattices, we achieve a transversal CCZ gate. And it was fun sort of playing around with these different types of lattices. I mean, it surprised me that these 2 separate rhombic dodecahedral lattices and this cubic lattice could sit nicely on top of each other so that they each meet at their faces. And so this is sort of a picture of the boundaries that we get. We get this parallel pipette. I've made a sort of a net. We did actually print this out and build a 3-dimensional model of this. But this is what the structure we needed to get the right boundaries. And we found that this particular example had all the properties we needed to gain this transversal CCZ gate. So now that we've found this universal gate for this code, this 3rd level of the Clifford hierarchy gate in this 3D surface code, can we build a full architecture for fault-tolerant quantum computing? Can this challenge the two-dimensional surface code? Well, let's compare them again. The reason this 2D surface code is so popular is for its very favorable properties. It has low weight error checks, this modular structure, a high threshold, and a convenient two-dimensional structure, which makes it easier to engineer. Three-dimensional is difficult because we need to control these qubits and we need to send wires in to control them. So having a two-dimensional structure is quite preferable for actually building these devices, although it's not necessarily essential. So it turns out that our 3D structure can indeed be made closer to a two-dimensional structure. And this was worked by my colleague Ben Brown, who's currently at Sydney. So he's also formerly of Imperial College. And what Ben realized was that he could take our construction and he could turn one of the spatial directions into a time direction. So rather than having this big three-dimensional code, you have these small two-dimensional codes which are slowly changing. I mean, essentially they move up the code. So you transform one layer into the next layer. And Ben showed that this preserves this property of being able to implement this transversal non-Clifford gate, but also that because the code was changing in time, the Bravyi-Koenig theorem no longer applied. So this is our way of achieving this fault-tolerant non-Clifford gate in something which is essentially a two-dimensional structure. So if we take these two models now, in the 3D surface code, we've got a two-dimensional implementation of it. We've achieved a universal native set of gates, and we don't require this expensive magic state distillation that was needed for the two-dimensional model. So the key disadvantage of our new model is the error checks are much higher weight. We had these weight 12, cube octahedra, which defined our error checks. And the error threshold is likely to be a little bit lower than the 2D surface code for that reason. Now the error threshold is something we're still studying, and ongoing work is going into simulating this, a full model of this, to find out precisely how well it works, what the error threshold is, and where the trade-off comes between the extra complexity we get in our 3D codes due to these higher weight measurements and some of the complicated extra steps that are needed to implement this mapping from 2D to 3D, traded off against the reduced complexity from removing the need to implement magic state distillation. So that's undergoing, that's current work. We're running simulations of this model, and the early results are quite promising. The threshold is lower, as one would expect, but not so much lower that it really, it would really completely offset this advantage. So it's likely that there will be some architectures and some error rates for which this three-dimensional to two-dimensional approach could be advantageous. So what else is there to study about these codes? Well, the geometric aspect of this is rather interesting. So we expected that this sort of relationship between the 3D lattices that we uncovered would be there in the literature, but we weren't able to find it. And it seems that in general, geometers have not been that interested in studying lattices with the kinds of boundaries, these rough and smooth boundaries that we need. So those rough and smooth boundaries are very natural for defining surface codes, but they're perhaps not so natural to study in their own right. So we're very interested to generalize this and see if there are other families of lattices with which we can implement the same construction, perhaps with lower weight checks that would give us an even better performance. So let me wrap up by giving you some references. So most of this work was joint work with Mike Vasmer, who was my PhD student, but is now a research fellow at the Perimeter Institute in Waterloo. And the ongoing work is in collaboration with Ben Brown, Tom Scrooby, my current PhD student, and our collaborators in Sydney, Stephen Bartlett and Paul Webster. But thank you very much for listening. I'm very happy to take questions now. So I didn't hear that. I think you'll need
Thank
to...
you very much for your
Thank you.
for your contribution. The floor is open to questions. You can unmute yourself. Maybe I can begin with asking the time. Switching to a time implementation and went very quickly there for me. Could you repeat?
Yes, it did. So I didn't go into the detail. So let me give you a flavor of what we do. So let me go back. Ooh. Let me go back a slide. So what we can do is, nice picture of the 3D. Yeah, maybe this is a good one. So in this three-dimensional structure, you can see that it's built up of two-dimensional layers. And actually, if we take a slice, a two-dimensional slice through the middle of the lattice, cutting across this membrane, what you find is you recover a two-dimensional code. So there's many copies of the two-dimensional code living in the three-dimensional code. And even better, when you take that slice, you save many of the error correcting properties. So this membrane operator turns into a string operator, but it's still, you can still use that for error correction. And so what this process does is it essentially works with these individual slices. It actually requires 2 slices at a time. So you're not going completely down to the original two-dimensional code, but you can take 2 slices at a time. And basically, there's a process where we can essentially sweep through the three-dimensional structure, adding a layer, then removing a layer, adding a layer, and removing a layer. And what you can show is that doing so preserves the error correcting properties, and it also preserves the structure of the logical operators that we can implement. Now, the really tricky thing then is actually doing this to 3 codes at the same time, and so that all of them work. And I was very skeptical that that was even possible, and Ben proved me wrong. And what you're able to do is apply that process, sweeping through. So here's his picture from his paper, sweeping through, this is just through a pair of these codes, sweeping through these two-dimensional slices, both of those codes, so that what you have realized has been equivalent to constructing the entire three-dimensional code and applying the gates between all 3 copies of the full code. So that's so it's
okay.
I was also surprised. I was surprised that it worked, but it does.
Yeah, thank you.
So what are the hardware challenges for this sweeping operation?
So there are a number. So this is, I said it's a mapping to 2D. It's not as two-dimensional as the 2D surface codes. It requires it requires multiple layers. So it requires a sort of flat 3-dimensional architecture. It is still modular in that within this structure, you're repeating the same sort of measurements over and over and over. So it's very similar to taking the 2-dimensional code and having 2 extra layers underneath and above, with some extra vertical couplings as well. So that's quite a significant extra structure that is not there in the 2-dimensional case. But having said that, the implementation of magic state distillation is also rather complicated. We avoid that aspect entirely.
And you have to implement some periodicity in the time dependence to get the lattice.
It's yes, it's a repeated process of it's a repeated set of operations.
And Graham, you have a question? Can you unmute yourself?
Yeah. Thanks, Dan. Thanks for a very nice talk. I was just wondering, you know, I mean, the Tolerant code sometimes people think of it as a Hamiltonian, you know.
Yes.
In kind of this kind of in condensed matter, and often even the Tolerant code itself arises as some kind of effective perturbative level from some maybe simpler or maybe more complicated model. Is there an analog to that here? Maybe where there's some kind of, where we can think of some kind of 3D Hamiltonian, where the operators arise as elements in that 3D Hamiltonian?
Yes, there is, and in fact, the 3D surface code has been studied more as a Hamiltonian than it has as an error-correcting code. So I don't have the citations in my slides, but they're there in our paper, and there are some interesting effects, because you have this these two different dimensionalities of or what we call in quantum error correction, we call them the logical operators, but the membranes and the strings and the way they interact in the Hamiltonian picture lead to some interesting physics. So that had been studied prior to our work, but relatively little quantum error correction work had been done with the 3D code.
Okay, thank you.
I was wondering, is there any possibility of doing it actually in 3 dimensions? Your lattices remind me a bit of perovskite.
So the answer is yes. Perovskite, that rings a bell. That's a crystal structure, is that?
Yes.
I think we certainly trawled through lots of crystal structures when we were writing this paper. So yes, so there are some architectures for quantum computing where 3D is no problem at all, and in particular, so the implementation of quantum computing with ion traps is an area where people have taken very seriously the idea of a 3-dimensional structure. So the problem with ion traps is that they're absolutely excellent for small quantum computers, but they're sort of limited by the physics of how they're constructed in the number of ions you can place in a single trap and perform computation on them. So you need to combine traps together in some way, and some of the methods that have been proposed for that work just as well in 3D as in 2D. So there are some particular proposals where 3D structure is very natural. In the solid state, people are less keen on 3D. I mean, solid state fabrication is a 2-dimensional process traditionally, although modern fabrication does incorporate 3-dimensional elements, but it's harder in the solid state, I'd say.
But would in principle this trick 3D to 2D would work like from 4 to 3, or it's already non-realizable, or just?
So that's an interesting question, and so it's not something we've looked in detail, but we think the answer is yes. Now, another question you can ask is, does this also work from 2 to 1D? And could you take your 2-dimensional surface code and reduce it to 1D? Now, it turns out that if you form the 1-dimensional analog of the surface code, what you get is simply the repetition code, the code that I started with. And the repetition code is a bad quantum code because it only detects one type of error. So it'll detect the Pauli X errors, but it won't detect the Z errors. And so the reason why everything breaks in that case is that your string-like operators, when you reduce the dimension, the string-like operators turn to points. And in some sense, you need the fact that these operators extend across the whole code. That is part of the robustness of the data storage. It means that to implement a logical Pauli error, you need to apply gates across the whole lattice. Whereas if that string is reduced to a point, then you lose all protection, because you can
yeah, but 3 to 4 it's different in a way. 3 and 4 it's in a way similar behavior, but 1 and 2 it's completely different. So
yes. Yes.
But it was not been studied.
No, it hasn't, and there is an interesting reason to study it, and it's on our roadmap. So there's a separate type of error correction which people have studied with topological codes, which is called self-correction, and this is when you form the Hamiltonian version of these codes. You turn these check operators into terms into a Hamiltonian, and then the errors are represented by energy penalties. And then you could imagine a thermal process where the thermal processes would tend to would be where adding errors creates a thermal barrier, and that these systems would naturally be robust and able to preserve quantum information over a long period of time. Now, that structure does not work in 2D because of the string-like operators. And essentially, once you've created an error in one place, there's no energy cost to increasing the size of that error, essentially. But when you have these membrane-like operators, then the energy cost essentially grows with the area of the membrane. So it's been shown that in 4D, this self-correction property does occur. So if you could build a 4D lattice, then you could, with this Hamiltonian, you could implement self-correction. It would be an intriguing prospect to try and drop a dimension down and try and implement self-correction here. But there's a lot of barriers for doing that, because the self-correction process is not a quantum circuit. It is just the ongoing Hamiltonian dynamics of a lattice. So there are barriers there, but it would be interesting to explore these. It's still an open question whether self-correcting codes in 3D are possible.
Yeah, thank you. It's very interesting indeed.
Thank you.
Hello. Can I ask a question?
Yes, go ahead.
Hi, I'm Alex Bliven. So thinking about the Hamiltonian version of these models, they usually arise as kind of topological phase of matter, right? You have an underlying description. Kind of taking these ideas, in the TQFT world, you also have like homotopy quantum field theories.
Yes.
So you can have TQFT with local on-site symmetry or something like this. Do people ever consider these codes in the homotopy field setting? There's some additional
So that's a good question. So there has been some work, but rather little actually, to take many of the weird and wonderful TQFTs that have been proposed and translate them into codes. So it has been done for some of the quantum doubles, but I'm not aware of it having been done for the codes that you're talking about. It would be interesting to explore that actually. I mean, in general, the mappings between these error correcting codes and the Hamiltonian systems are very natural.
Yeah, it seems like the technology to do that has actually been developed in the past few years from the TQFT perspective that make that quite an accessible thing to try now. That'd be interesting. Yes,
that would be, because you know, different Hamiltonians with different physics could certainly lead to different error correction codes with different properties. And we're very attached to these codes that are defined by Pauli operators, and they tend to map to Hamiltonian models based around Z2, which are often the most boring models that don't get studied very much. When you move away from that, you move away from Pauli operators, and you often move away from qubits. And so new techniques are needed, but it can certainly be done.
Because one thing you could do that still seems Pauli would be, if you're taking the surface code, this is like 2D toric code with gapped boundary conditions, right? And so you could imagine having like a lattice with vertices being like gapped bound, like bounded by gap boundary conditions, and then having 2D lattice coming off. And if you solve this in the TQFT setting, then what this is it's a Z2 toric code with a Z2 symmetry enrichment. So you have the Hamiltonian. And it'd just be interesting to see how you could use this duality. So you have like on the side Z2 symmetry protection as well as like topological order. And would this give you like a higher threshold than just having the topological order?
Yes, that would be very, very interesting. So this is yes, that'd be very interesting to explore.
Maybe we could talk. I spoke to one of your PhD students like a year or so ago in Leeds, and he was asking questions that was somewhat related. I can't
was that Tom?
Whoever came to visit Leeds in the past year.
Yes. I also I've got some ongoing projects with Yanis Pakos, and yes, these sort of questions are the things we've been discussing, but we haven't looked at that in particular.
Okay. Do we have other questions?
Well, at the beginning, you said these are interesting times. So, what do we expect as next steps, and where do you expect them to happen?
So I think, I mean, the next, so there's going to be a lot of focus on NISQ and NISQ quantum computing over the next few years, and things will progress quite rapidly, I think. I mean, there's tremendous competition. And so what they're trying to do is make larger devices with more qubits, but with less noise. And that will enable them to implement a number of algorithms. So there are a number of quantum algorithms which are not so sensitive to noise that they won't work if there's any noise at all. So Shor's algorithm is not in that category, really. It needs everything very sort of nicely error corrected. But there are other sort of simulation algorithms which are not in that category. So, I mean, I think what we'll see over the next few years are more competition to Google, other teams around the world having 50 to 100 scale quantum computers, and a real competition on driving the noise levels down to start to implement some simulations which can do interesting things which are beyond the capabilities of classical computers to simulate.
So do you really think that 100 is within reach?
Well, yes. I mean, that's what they tell us. These groups. I mean, there's the proof is in the pudding, and so in some sense, anyone can build a 100 qubit quantum computer that doesn't work very well. Even I could do that. But so you have to take the announcement with a pinch of salt. But they show you this is very, very difficult, but it shows you what people are aiming at. So, for example, Rigetti, who are a startup who've grown quite significantly, they have promised an 120 qubit computer. It's certainly on Google's roadmap to continue increasing the scale. But they know that there's no point in doing this unless they can also reduce the errors. So that's what's stopping. They could build these devices tomorrow and have a bad device. So it's expanding and controlling the errors at the same time, which is really hard. And it's sort of why we didn't immediately see groups around the world copying Google and having 50 qubits. It's that battle that is going on in the research and development.
So Rigetti has actually promised 100 qubit NISQ machine in the UK at Tubney Woods with Oxford Instruments within the next 3 years to generate some non-trivial optimization algorithms. So we've got them under contract, so they better deliver.
Okay. I mean, 3 years seems a feasible timescale.
Okay. Tom, I think you have a question.
Yes, I was going to ask about what do you have to do mathematically to find out what the tolerance for error is? I mean, you want to allow for errors, but what do you have to do mathematically?
So there are different methods. The most widely used method is you just run a simulation, and that's. Let me go back to my threshold. So you can run a simulation and generate data like the data in my threshold plot. And what you're looking for is both a crossing in the probability of successful error correction versus the error rate. And you want that this probability is increased as your as the size of your lattice increases. So that's one way of identifying and estimating a threshold numerically. But there are also rigorous ways.
Yeah, that's what I was going to ask about. Yeah.
And these methods, and the beautiful thing is that a lot of these problems can be mapped into classical statistical mechanics problems, and then they arise as phase transitions. So, for example, the thresholds for the 2D toric code were obtained by a mapping to the random bond icing model. Mm-hmm. Now, the thing I don't like about the thresholds that are calculated that way is usually in order to get the statistical mechanics model to be something usable, you have to use quite an idealized error model. And if you use a more realistic error model, typically it won't correspond to a nice statistical mechanics model. So there you're sort of stuck in the realm of numerical simulation. But certainly in the early days of studying these codes, a lot of progress was made by mapping the models into statistical mechanics models. And then you can, once you've made that identification, often someone would have already calculated the phase transition points. I mean, it's sort of remarkable that I think just almost about the same time that the toric code was proposed, someone had computed, I think it was Nishimori, had computed the phase transition point of the random bond icing model, which gave them the threshold. And that was done independently just at about the same time that the code was proposed.
Thank you very much. Very nice talk.
Yeah. The nice thing about Shor algorithm thing or prime factorization is that you have a clear benchmark.
Yes.
For quantum simulation, it would be very useful to have something similar, some problem where one really can check if you can do something which is of interest to other people in contrast to what has been done at Google. Is there something which is under discussion?
So very much so, and this question of benchmarking and verifying quantum simulation is very much under active research. And in fact, I'm engaged in a collaboration where I'm not personally working on that particular question, but our colleagues in Bristol, Noah Linden and Ashley Montanaro, are. And it's a very interesting question. How do you benchmark and check something that you can't implement on a classical computer? And there's a variety of methods people use to explore that. So some things is you can sort of have a test simulation which has special parameters which are chosen so that you can simulate them efficiently. So you can imagine maybe you're trying to explore some phase diagram, and there's some points in the phase diagram where you've got an analytic solution. So those are the sorts of things you can do. But there are other ideas which sort of use ideas from cryptography, where you can sort of see, you sort of deliberately try and corrupt the output in a certain way and look for the signatures of that corruption, which again would be a signature that the overall process was performing correctly.
Do you expect that something universally recognized benchmark will come up soon?
That's a good question. And I don't know. As I said, it's very much work in progress. I mean, certainly this is very much desirable. And there's a lot of discussions at the moment on sort of standards for quantum computing. I mean, it's becoming a marketplace. So how do you actually, officially characterize what you're selling? But it's still in the verification side. I think it's still very much work in progress.
Thank you.
Can I ask a bit more detailed about these errors? So
yes,
when the bigger the error correcting circuit you build, you also get the chance of having errors within that again. Isn't that right? So you're taking that into account when you're doing the interview.
Yes, you take that into account. And one of my comments earlier about error models relates to that point. So the simplest error models, the ones which are most amenable to mapping to statistical mechanics models, don't do that. Whereas in a full simulation, you can indeed simulate all of the errors in all of the devices. But it was from, it's a long tradition of fault-tolerant quantum computing that you assume that all of your components are faulty, and there are certain approaches that are used, such as this construction of transversal gates, which ensures that even though everything is faulty, the errors don't propagate too much, and somehow the local structure of the surface codes are advantageous from that respect. So, for example, in your measurements, to detect all these errors, there will be errors in those measurements, but because the measurements themselves are localized to a small number of qubits, the errors that those processes create are also localized, and the code itself is very good at correcting for errors that are localized to a small part of the lattice. So as long as all the errors are below the threshold, it's very robust into different types of error.
So are you always assuming that there are individual qubit errors which are basically independent?
So they don't need to be completely independent. So in much work on error correction, this is a working assumption that the errors are independent, but yes, it can be relaxed. And on topological codes, as long as the correlations between the errors are small compared to the size of the lattice, they don't need to be completely independent. Which they're not in the realization. These errors are not independent. There's a lot of crosstalk errors, and yes, the sorts of control pulses which are realizing a gate on one part of the chip are being felt across the chip. So,
well, thank you very much. It was a very interesting talk.
Yeah, thank you, Robert Lynn. I think you have a question.
Thanks. Yeah. So you mentioned that when you calculate the threshold, there's a number of error models that you can assume. Is there, do you know of any work that uses the depolarizing channel?
Yes. So the depolarizing channel is probably the second most common error channel that's studied in the study of these codes. The reason it's not the first most common is that the easiest types of errors to study are errors where X errors and Z errors are entirely independent. But yes, depolarizing noise it's the simplest channel to study theoretically, which is sort of closest to what happens in physical devices, although it's quite far from what happens in physical devices, but it's a good model for a general noise process.
So what since I'm interested in this theoretical study along the lines of what Professor Spencer was mentioning with the threshold calculations. Do you know any of the work, particular people on this?
So yes, so one of my colleagues, Alex Kubitska, who so he's based at the Perimeter Institute and is working quite closely with Mike Vasma. He has worked quite a lot on this and has a recent paper with some general tools for constructing statistical mechanics models. And yes, indeed, it becomes more complicated. I mean, essentially, when you have depolarizing noise, the X errors and the Z errors are now correlated. So your statistical mechanics model now needs to include the X checks and the Z checks together in a single model. But yes. So there has been some work that's been done on that. And
thank you very much. That's very helpful. Thank you.
Do we have any other further questions? Well, if not, let's thank Dan for a very nice talk. Thank you very much, Dan, for this.
Enjoyed it.
Thanks. And I'm going to stop recording.
Thanks very much.